Okay, I think we'll get started. So today we're on the last of our labs for machine learning and general chemistry part 2. And in this one, we're going to go back to something we did in part 1, where we used convolutional neural networks to do image recognition. So we're going to now use an application where we are looking at the loading of chitosan-alginate bioplastics with dye. Now this is kind of inspired by work of another member of the Concordia chemistry department, and he's got some images of these bioplastics with various states of dye loaded on. In this case, it's a blue dye. So the biofilms themselves are essentially white or clear, and then when they're loaded with dye, they start to turn shades of blue. And so one thing that you might be interested in is having a machine learning look at the bioplastic, identify its loading level, its loading percentage, and then move it on to the next phase in whatever needs to be done. So we're going to be looking at, again, supervised learning. So I made a test set of 32,000 images of different levels of loading, and it was trained on that. That takes a long time, so we won't actually train. We'll see the results of that training. So that was a 32,000 image set. And then we'll be using convolutional neural networks, which I'll talk just a little bit about. I talked about it more in the lab on convolutional neural networks in part 1 of this series. The chemical application here, again, we've got this bioplastic film, and we can, by sticking it in a concentrated solution of dye, it will pick up the dye, and then that can be placed in then either pure water or some other, and it will release that dye. So there'll be various applications of this where maybe instead of a dye molecule, you have some important drug molecule or something to be loaded onto these bioplastics and then released under different conditions. So, important area of chemistry that is studied. Let me just review very, very quickly the convolutional neural network idea. So in a convolutional neural network, at each stage in the network, there is a set of masks or filters that are designed to pick out specific features of an image. Now here we're looking more at the color of the image, but I think it's easier conceptually to understand with the shape. So you can do shape or color, anything that you can sort of quantize and then build some sort of mask out of. So imagine a mask here that has a single vertical open space like this. And a convolution means just take one function, or in this case the mask, and run it past another function, and in this case the object. So we're going to run this mask past this object, and we would see that when this mask lines up with this horizontal line, it will get a strong signal. Everywhere else it would get a weaker signal. And so we would say that at that position in this image we have a strong indication of a vertical line in that position. Then another mask might be this horizontal. So if we send this across, I think in this case we go this way. We can go we can convolve in all directions. So we would convolve this way, and we would see this light up more so when that overlapped that mask there. So by having a whole array of masks, you can get a pretty intricate picture of the image. And then the next layer has more refinement and more refinement and more refinement. Now there comes a point, as we've talked about throughout this series, where you might overtrain on a data set, and then it's less able to extrapolate beyond those data. So part of the art of doing machine learning in chemistry is finding the right balance of not undertraining and not overtraining, but trying to hit it ideally. All right, this seemed to work fairly well. We get decent results, so let's go look at that. Okay, so let's start with the lab manual here for this lab. Again, this is a lab based on the work of Graham Wiley and the Concordia Chemistry Department. And it's looking at these chitosan-alginate bioplastics that are able to have an equilibrium with different molecules such that they can come off and come on. So they don't get stuck on permanently or they don't not come on at all. So for certain molecules, that is the case. And he's been doing a lot of preliminary work with different types of dye molecules because it's very easy to track the color of those dye molecules. We kind of talked earlier about some of the applications there. You can imagine if you have something that can hold and then release, there might be a lot of medical applications for delivering drugs, but also other environmental usages. So pulling in, say, certain compounds out of the environment and then dumping them in a way we can keep them sequestered. Again, supervised learning, so that is, I gave this big training set and told it the level of loading, and then so it knew the level of loading, and then it identified that image, and then the next image knew the level of loading, identified that image. So that's supervised learning. Earlier, we had seen the unsupervised learning with with both the robot and not the robot, but with the hydrogen bonding case in the earlier labs. Okay, so in 32,000 images was the training set. So let's go ahead and open this. And so we'll click on the Bioplastics link. Again, this will come up, but you can close that, or you can not close it. You got to keep it open, but you can minimize it. And again, takes a little patience. It's got to load the actual results of that training set. So this one takes a while to load onto your machine, depending on your speed of your computer. So I always start to think it's not coming up, but we'll see here. Hopefully it will. Okay, finally came up. Okay, so pretty simple task here. I'm going to see if I can make that a little bigger. And I don't want to go so that I cover this. It's about right. Okay, so what we're going to do now is we are going to put in the time in hours that the bioplastic has been placed in the solution of dye. So we're going to start with 0, and we'll simulate that load. And we get a picture here now. This shows what a typical bioplastic looks like when it's completely unloaded. What we're going to see here, and this will be different for you, it's different every time, is the predicted is blue and the real value is gray. So in this limit here of not very loaded, it didn't do the greatest job of predicting here. And this is worse than I've seen in the past, but we'll see here now. Let's go 0.1 of an hour. Now it's right on top. That's a kind of a good, got that one exactly right. And again, yours will be a little different. Every time we run, it'll be a little different. Let's see. I'll just follow what we're told to do here. So 0.3, whoops, 0.3. Again, we're starting to see the real is gray and the guess by the computer is blue. 0.5. And I'll just do a few more here quickly. 0.8. Oops. And 1. 1.5. Still doing quite well over a big range of loading because it was trained on a fairly robust data set. You can see up here starting to look a little more blue, so about 50% loaded here. Let's go to 2 will continue to look more and more blue. 2.5. 3. 3.5. 4. 5. Now it's looking quite blue here. It's reaching about its maximum load, which is about 70%. 6, 7, 8. Now we're looking for some systematic errors. Notice, and I think this is probably what you're seeing too, maybe not, maybe a little different, but that we're underestimating here at the high loads, and we were, in this particular case, we overestimated at the low load. And then 11, I'll just do a few more here, and 15. And so we see kind of a typical loading curve. So chemically, this is sort of reasonable to expect that you would dump, it would pick up dye just kinetically a little bit faster early on. So kind of a typical kinetics curve, and then it'll level off at some level depending on the dye and depending on the bioplastic. So that would be related to the thermodynamic equilibrium constant of the dye absorbing into the, or adsorbing onto the bioplastic. All right, I think that is about it for walking through this lab. So a good application of this convolutional neural network. Again, it is looking at the image. It's not given any numerical information about the image. It's simply looking at a whole bunch of images of different loading values. And then it's trying to predict the load by looking at a new image. So what it's seeing up here is a new image. Maybe should have been a little more clear with that. What it's seeing up here is a new image presented to it that wasn't in its training set. And then it's making a guess as to the loading, and then the gray is what it actually is, which of course we wouldn't know, but you want to test that on stuff you do know so that you can build some confidence. And so at least to a certain, it's not perfect, but to a pretty good degree, if we had a little camera with some AI machine learning placed on it with this this training set loaded, it would do a pretty good job of capturing the degree of loading on this bioplastic. All right, that's it. So, I think, shoot, I was off the bottom here, maybe. So hopefully not. In case I was off the bottom there in the graph, time on the bottom here, load over here. All right, that's it. I'll stop recording here.